When a user swipes through an infinite feed, the next video locks into place and begins playing instantly. This immediate playback is defined by a strict engineering metric, time to first frame, or TTFF. For a seamless experience, the TTFF must stay under 300 milliseconds. Hitting this latency target across global, highly variable mobile networks is not a front-end UI trick. It requires solving a massive distributed systems problem. Traditional video-on-demand platforms like YouTube or Netflix are built on the assumption of predictable, sustained user viewing sessions. You click a video and you watch it. Delivering an infinite scroll feed means abandoning that traditional streaming architecture entirely. It requires replacing static delivery with real-time prediction and dynamic edge routing. This diagram shows standard sequential buffering. A video player fetches data over an HTTP/TCP connection as fast as the network allows and fills a single client-side buffer from left to right. This sequential queue absorbs network fluctuations, preventing rebuffering events while a long video plays. An infinite scroll feed introduces a failure mode. Users swipe at unpredictable intervals, abandoning the current video. When a swipe occurs, the system is forced to discard that heavily prefetched data. The buffer drops, and a new queue begins from scratch. Across billions of sessions, this results in 40 to 60% of downloaded data being wasted. This inflates CDN delivery costs and drains client mobile batteries. Relying on traditional buffering for short-form content breaks the economics of mobile networks. Surviving the swipe necessitates a predictive prefetch model. Before a video is served, it must be ingested. Millions of creators simultaneously upload massive, high-fidelity mezzanine files over unstable cellular connections. To manage this, the ingestion pipeline utilizes the QUIC protocol to decompose the media payload into small, concurrent chunks. When packet loss occurs, QUIC isolates the failure, triggering a retry only for the specific interrupted chunk, leaving the transfer intact. Once those chunks reach the edge gateway, the system executes a fast preview first, heavy processing later workflow. The edge server splits the data, generating a low-resolution preview for immediate cache distribution and wraps the raw file into Kafka. Kafka acts as a shock absorber during traffic spikes, queuing the heavy raw file for asynchronous, multi-bit rate transcoding. This asynchronous pipeline removes upload friction. The video enters the recommendation feed instantly via the preview, while intensive back-end processing completes in the background. Once the video is live, the architecture shifts to the recommendation engine, the core system deciding which video fills the next 300 millisecond window. Traditional machine learning models map sparse categorical features, like user IDs and hashtags, into dense vector representations. To map these growing categorical inputs, engineers historically use a fixed-size hash table. But at global scale, this inevitably leads to hash collisions. Distinct user profiles collapse into the exact same embedding, degrading the accuracy of the recommendation model. To solve this, ByteDance engineered the monolith framework, built specifically to handle sparse categorical parameters without accuracy loss. Monolith abandons the fixed hash trick and utilizes a collisionless embedding table powered by cuckoo hashing. If a collision is imminent, it dynamically kicks the existing embedding into an alternate, empty slot. Every user and item maintains a unique numerical representation. Accurately modeling real-time, non-stationary user behavior at global scale mathematically requires this collisionless embedding. Back on the client side, the player must intercept the recommendation engine's output without falling into the trap of sequential VOD downloading. This is controlled by the Gamora prefetching framework. Gamora uses deep reinforcement learning to dynamically calculate current network throughput alongside the user's probability of swiping. Gamora replaces the single sequential buffer with active management across multiple parallel short video queues. Each queue operates on an age of information, or AOI, threshold. This metric dictates exactly how much of a current video must be buffered before playback is safe from rebuffering. Once the active video reaches its dynamically calculated AOI threshold, the system intentionally suspends the download. The reclaimed bandwidth is instantly redirected to fetch the first segment of the next video in the queue, prepping it for a potential swipe. Active buffer management resolves the data wastage paradox. It guarantees the next video is ready in under 300 milliseconds without downloading unseen content. Now trace a single user interaction through the fully assembled architecture. The user swipes. A WebSocket post request fires from the client, instantly streaming the micro-interaction. The monolith engine ingests the signal, updates the collisionless embedding table, and generates a fresh batch of sorted video candidates as URLs. Dynamic routing intercepts the response, directing the client to the optimal edge server based on real-time ISP latency. The Gamora framework receives the URLs, calculates the bandwidth, and fetches only the necessary initial segments into the active buffer. From client swipe to machine learning inference to edge delivery and into the client buffer, this entire traversal executes reliably in under 300 milliseconds. Short-form video forces a hard break from the foundational protocols of internet media delivery. Standard delivery networks fall short. They must be replaced by continuous, real-time prediction models across both the network layer and the recommendation layer. Balancing data economics with zero-latency playback is the ultimate test of a modern distributed system. The frictionless infinite scroll experience is an illusion. It is sustained entirely by a rigorously orchestrated pipeline of active buffers, asynchronous ingestion, and collisionless machine learning.